Imagine a detective arriving at a crime scene, cracking the door open, looking inside for exactly 1 second, and declaring the case solved. It sounds absurd, but human beings are naturally wired to think this way. We tend to favor Occam's razor, the idea that the simplest, cleanest explanation is usually the correct one. Machine learning engineers frequently fall into this exact trap. They often lean towards simple algorithms because they require less computing power, they are fast to deploy, and they are easy to explain to stakeholders in a boardroom. But what happens when you take a highly nuanced, messy, real-world problem and force it into an algorithm that is inherently too simple to grasp it? In data science, this failure state is called underfitting. It happens when an algorithm's rigid assumptions make it completely blind to reality, proving that a glance too brief misses the evidence that actually matters. To understand why underfitting happens, you have to look at a structural property called model capacity. Think of capacity as an algorithm's mathematical flexibility, its ability to bend and fit a wide variety of data shapes. This animated graph shows a low-capacity model. It relies on a basic linear equation. No matter how much data you feed it, it is mathematically locked into seeing the world in perfectly straight lines. Now let's drop in a complex dataset representing a nonlinear relationship, like how body mass index relates to different exercise levels. The data clearly forms a curved U-shape on the grid. As the model tries to learn, it faces a physical impossibility. Its strict linear assumptions, what statisticians refer to as bias, prevent it from tracing the curvature of the data. Those massive gaps between the straight line and the data points represent the model's predictive blind spots. Applying a simple model to a complex problem doesn't give you a safe, conservative baseline. It creates a structurally invalid tool that completely misreads the geometry of the situation. In the 1960s, early computer scientists were incredibly optimistic. They believed they were on the verge of cracking artificial intelligence, using highly simplified linear models running on these early mainframes. Then, the entire field hit a brick wall. They encountered the XOR problem, a foundational logic puzzle requiring a system to understand intersecting nonlinear conditions. The linear models failed the XOR test entirely. They simply did not have the mathematical capacity to draw a boundary around nonlinear rules. Prominent critics like cognitive scientist Marvin Minsky seized on this specific structural blindness. He argued that early, biologically inspired neural networks were deeply flawed because of these limitations. The realization that these models were underfitting reality caused a massive freeze in government and private funding known as the AI winter, stalling technological progress in the field for decades. Today, data scientists have to catch these rigid models before they reach the public. How do they prove an algorithm is underfitting in the lab? They use a standard diagnostic test, visualized here with 2 gauges. They compare the model's training error, its performance on the exact data it studied, against its test error, which measures how well it handles brand new data. In a severe case of underfitting, the model is so rigid it can't even memorize the data sitting right in front of it. As a result, the training error spikes high into the red. Because it never grasped the foundational patterns during practice, its performance on new data is equally disastrous. The test error immediately spikes to match. When both gauges are high, the model failed to learn the subject at all. It acts like a student who refused to open the textbook all semester and predictably bombed the final exam. If an algorithm refuses to learn, engineers have to step in and cure it. The solution is to increase the model's capacity. By adding more layers and parameters to the neural network, engineers give the system the mathematical flexibility it needs to abandon its rigid assumptions. Looking back at our chart, that inflexible straight line shatters. The model reshapes itself into a smooth, elegant curve that successfully intersects the real-world data points. To build algorithms that function in reality, we must let go of the illusion of simplicity. We have to give machines the capacity to look closer at the evidence. But watch what happens to our chart if we keep increasing that capacity without any limits. The smooth curve starts vibrating, turning into a chaotic, jagged line that contorts to memorize every single piece of random noise on the grid. Underfitting is a dangerous form of algorithmic blindness. But giving a machine the capacity to memorize absolutely everything creates a completely different, and arguably worse, kind of disaster.